Hello, everyone, and welcome to the lecture notes for Chapter 10, Part 2, Rigid Body Rotation about a Moving Axis. And I refer people taking my class to page 9 of the notes. So up until this point, we've been dealing with either objects which are spinning or objects which are moving in a straight line. And we've also talked about things falling down some kind of a ramp. We've treated them as a box or a block or something where you're just worried about the forces through the center of mass. Of course, this doesn't describe a lot of the things that actually happen in our lives, like wheels and balls and just generally round things, which as they go down a slope will both roll, for instance, in this direction, and they also will be translating. They will be falling down the slope as they do so. So how do you account for the rolling motion as well as the translation motion? And that's something that we're going to talk about in this part of the lecture. So let's look at a rotating object which is also moving through space. So let's say that we have a baton that is twirling through the air. And what's happening is that the center of mass here is moving through space in both the y and x directions, while at the same time there is a rotation about that center of mass. So you can think of a rotating object moving through space as having two distinct types of motion which are interrelated. There is a translational motion and a rotational motion. The kinetic energy of that rotating and translating rigid body is, as you would imagine, simply an addition of the rotational kinetic energy, which is what we see here, or 1/2 I omega squared, plus a translational component, which is the linear kinetic energy of 1/2 mv squared. So this is the linear component. That's not how you spell linear. This is the linear component over here. And this is the rotational component over here. And there are two different kinds of kinetic energy. There's the kinetic energy that is stored in the ball or whatever round object you have moving in a straight line, and then the kinetic energy in that ball that's actually rolling and rotating. And as we're going to find out, the forces that are acting to get a ball rolling, to get the ball rolling, as it were, can be somewhat different than the forces that are involved in getting the ball actually moving. All right, so the motion of a rolling wheel is the sum of the translational motion of the center of mass plus the rotational motion of the wheel around that center of mass. And the condition for rolling without slipping is that the velocity of the center of mass is equal to the radius of that wheel times omega, the angular velocity, or the velocity that's happening in a circle. Now that's a condition for rolling without slipping. You can have something which is known as a slip, and that is something where you can think of, say, locking your wheels. If you're driving on an icy surface and you slam on the brakes and you don't have anti-lock brakes, the wheels will lock and your car will skid. And that's not what we're talking about here. We're talking about basically a case where the rotational motion is keeping up with the translational motion. So in other words, you are not moving in a line faster than you are actually rotating that particular wheel. And the condition for that to happen is that the velocity of the center of mass is equal to the radius times the angular velocity. So this is just kind of an illustration of what's going on. You have these 4 points here, and they're moving in a straight line. That's the linear portion. That's a translation of the center of mass. There's also rotation about the center of mass. So there's a velocity that's going this way as well on each of these points. And if you sum them together, the combined motion is going to be these velocity vectors. You have one that's 45 degrees above the horizontal, one that's 45 degrees below the horizontal, and then this one is actually moving at 2v going this way, and the wheel is actually instantaneously at rest where it contacts the ground. Okay, but this is just sort of what we're looking at. So we're not worrying about slip. We're not worrying about a case where the ball is bouncing. We're just thinking about a case where the wheel is basically keeping up with the linear speed. So again, two types of kinetic energy. The rotational kinetic energy, and that's 1/2 I omega squared. Um, And then there's a translational kinetic energy due to the translation of the center of mass. Let's remember our condition, again, for rolling without slip. So just a reminder, let's put that down there. What we see is 1/2 mv squared. If we make the substitution for v squared, that v is equal to r omega, so that substitution goes in there, we end up with 1/2 mr squared omega squared as being the translational kinetic energy. So one thing you'll notice here is that the energy, the kinetic energy that's contained within a moving object or within a rolling object is split over a rotational component and a translational component. What defines what percentage of each that you actually have? So in other words, what fractions of kinetic energy and rotational energy are you seeing? That is actually going to depend on the moment of inertia of the center of mass. So what we have here is if you have a hoop and you have basically the concentration of mass at the outside of this hoop. Yeah, so you have a lot of mass here at the edge, and you got basically this big donut in the center. The moment of inertia is given by mr squared, and the fraction of the kinetic energy that's in translational motion is 50%, and 50% of it is going to be in rotational motion. In a disk, where instead you have something that's solid all the way through, looks like a frisbee, or is a frisbee, or something along those lines, the moment of inertia is 1/2 mr squared, and the amount of energy that's in translation, in other words, the amount of energy that's happening in the linear motion, is 67%, whereas only 33% is taken up by the rotational motion. And finally, with a sphere, you have 71% of the kinetic energy being in translational motion and 29% of it being in rotational motion. Where exactly do we get this from? You'll see this in just a minute. There is actually an example that we'll get into later in this video that will explain where this comes from. But one thing that you can kind of notice, or maybe take to the bank, is that if you have a high moment of inertia, and this is a high moment of inertia, it's 1 mr squared. It's not a fraction of m, it's mr squared. You'll notice that because you have a higher moment of inertia, there is more resistance to rolling. That's kind of the way that you can think of a moment of inertia, is how easy or difficult is it to get the thing rolling. And if you have a greater resistance to rotation, more of the kinetic energy in that system is going to be taken up in the rotation. As opposed to if you have a sphere where the rotation is relatively easy, because the moment of inertia is smaller, you're going to have less kinetic energy tied up in that rotation. All right, so just something to kind of keep in mind here. And the more mass is distributed farther from the center of mass, the more the percentage of rotational energy. So again, if you think about those wands, the red and blue wands, there is more rotational energy in two masses that are spaced far apart, as opposed to the same two masses being very close together and being spun. Okay. All right, so let's take a look at what this means in practical terms. Let's say that we have three objects that start at the same height. We have a hoop, a disk, and a solid sphere. So what's happening is there is some quantity of potential energy given by mgh, which is converted entirely into kinetic energy, which is 1/2 mv squared plus 1/2 I omega squared. Okay, so let's say that we have that particular case going on. what we want, or if we want, greater speed, if we want this ball to get to this ball or hoop or disc or whatever, to get to the bottom of the slope faster, would we want to have a high rotational energy or a high translational energy? We would want to have a high translational kinetic energy because then you have a higher linear velocity, a higher translational velocity. And if you have a higher translational velocity, that means, well, that means that the thing's going faster, which means that it's going to cover a particular distance in a shorter amount of time. So the object that is going to be moving fastest is the one with the least percentage of k rotational, or alternately the highest percentage of k translational, and that's the sphere. The object moving the slowest is going to be the one with the highest percentage of k rotational, and therefore the lowest percentage of k translational. And in this case, that's the hoop. And one thing that we're going to see in the next few slides is that this is actually irrespective of mass. And that's going to be kind of a bit of a surprise when you think about it. Where if you have hoops that are made of a heavier or a less heavy material, they're all going to reach the bottom of the slope at the same time. All of the spheres will reach the bottom of the slope at the same time, and all the discs will reach the bottom of the slope at the same time, but kind of spaced out like this, assuming that they have the same radius. All hoops of the same radius will reach at the same time, and also assuming that their moments of inertia, or that the moments of inertia of, say, the hoop is all the same. So if you had, say, a hoop that was slightly thicker, then you might see a difference. But if they're all the same kind of thinness, it's irrespective of mass. And we'll see that this is actually the case, again, in just a few slides. All right? So that's pretty cool. So let's figure out exactly how this happens. So what exactly is going on when an object rolls? So what we want to do here is we want to calculate the acceleration of a center of mass. And we're talking about a round uniform body of radius r that is rolling down a ramp. This is kind of analogous to the old, box on a slope problem that we've seen again and again and again and again in this course. But there are a few differences and a few subtleties which make handling this as a ball, or handling this ball rolling down the slope, slightly different. Okay, so let's start with kind of the easy part. We have the force of gravity, or the weight, pointed straight down in this case, and then the angle of the tilt theta is given here. You know that the weight is going to have an x and a y component, and that y component is going to be given by the force of gravity times cosine of theta, that's represented here. And there's also going to be an x component of weight, which is Fg sine of theta. That corresponds to this guy over here, and that's that guy over there. So far, so good. And then we're also going to see a normal force, and the normal force is pointing up perpendicular to the surface and is going to be equal in magnitude and opposite in sign to Fg cosine of theta. And this is because there is no acceleration in the y direction. This ball is not hopping off the plane. This ball is not getting ground into, accelerated into the slope. It's just there. There's no net force and no net acceleration in the y direction. So if we're saying, okay, what are the balances of the net forces in the x direction? We say, okay, we've got, this x component of gravity, or x component of weight that's going in this direction, and the opposite direction we expect to see friction. But there's a slight difference. Previously, when we were dealing with friction, we were drawing the force of friction arrow through the center of mass. But that's not really what's happening here, right? I mean, this whole surface is not contacting anything, and therefore there should be no friction. The only friction that we see is where the ball is actually in contact with the ramp. And you'll also notice that the force of friction is pointing, up the ramp in the opposite direction of the ball's motion. But this should also suggest something to you. is that we have that there's a ball, and friction is kind of dragging it. It's kind of moving that ball in this particular direction. And let me see if I've got. Unfortunately, I don't have a ball handy. Sort of wish that my home office was a little better enabled for these demonstrations. So let's pretend that this stapler is round for a moment. And friction is acting on just this bottom portion of the stapler. And that's going to cause the stapler to rotate. So the friction is actually exerting a torque on this particular ball. And that's important to note, and it will become important to note as we go about trying to solve this problem. So let's go about trying to solve this problem. The sum of forces in the x direction is equal to ma sub x. Boring, we've done that before. And we know that the sum of forces is going to be negative mg sine theta plus the force of static friction is equal to negative ma sub x. Why did we set the signs this way? Well, in this particular problem, we are defining the positive x-axis as being over here. So it's going up the ramp. That's what we're calling positive x, or that's what the book is calling positive x. So this force, Fg sine theta, or mg sine theta, will have a negative sign because it's going in the negative x direction. The force of friction will have a positive sign because it's pointed up the ramp in the positive x direction. And the acceleration is going to be negative. So the acceleration is this way, going down the ramp. And that acceleration is in a negative direction, and therefore ma sub x is going to be negative in sign. Okay, that's good. And then we can go ahead and sum the forces in the y direction, and we know that it's the normal force minus mg cosine theta, and that's equal to 0. So ordinarily, if we were dealing with some kind of a ball or something like this, we'd say, well, you know what the normal force is, and you can calculate the force of static friction very easily by simply saying that the force of static friction is the normal force times the coefficient of friction. What is the coefficient of friction? Oh dear, I didn't give that to you. So we don't actually know what this is yet. This is an unknown. We're going to have to figure out what that is. We also have here this other unknown, which is ax, which is what we've been asked to solve for. So we have two unknowns, but only one equation. So how do we solve that problem? We're going to need another equation, and that is going to come from recognizing that the force of friction is giving this ball a torque. It's giving it a turn. So what do we know about torque? We know that the torque is equal to the moment of inertia times the angular acceleration, right? We also know that that torque is going to be equal to R F sub S. This was a note in the previous lecture series, or the previous set of lectures in Chapter 10, Part 1, I believe, where you were talking about the definition of torque as being a force times the radius of the object on which the force acts. So we make that substitution in for the sum of the torques. There are no other torques. There's only the torque of friction going on here. And you have a moment of inertia times the angular acceleration, as that's the definition for the sum of torque. All right. So we say, okay, but what's the tangential acceleration going to be? And you'll note, very conveniently, that because the torque is acting in this direction, the angular acceleration is also going to be in this direction. And that's going to be in that direction. So that's going to be a tan, which just happens to be the same acceleration as the ball is going to have. Okay, it's in the same direction, and we are also very soon going to find that it's the same magnitude, and I'll explain why it's the same magnitude in just a moment. So we can say that the A tangential is equal to r times alpha. All right, and that allows us to solve for alpha, that being the angular acceleration, as A tangential over r. Okay, so if we take this guy over here and we plug it in over there, we end up with rf sub s equals I times A tangential over r. And if we move this r, if we take this r and we put it over to this side, we end up with the force of static friction is equal to I, the moment of inertia, times A tangential over r squared. And then what we say is that the tangential acceleration is equal to A sub x. Why is that? Well, think about this for a minute. If you had a circular object, if the acceleration of the rim is faster than the acceleration of the thing in the center, you're going to get some kind of tumbling motion. The velocity of the center of mass is then not going to be equal to r times omega, and then you're going to see some kind of slipping. All right. Similarly, if the acceleration of the center of mass is faster than the acceleration of the rim, if that's moving faster, then again, that's like if you lock the wheels on your bicycle or on the wheels of your car and you get a skidding. That's where, again, the center of mass, we're getting more translational acceleration than you are getting rotational acceleration. And in this case, no slippage is occurring. So for no slippage to be occurring, the acceleration of the center of mass and the acceleration of the rim have to be equal in magnitude. And as we can see from the direction of the torque, the acceleration is going to be in the same sign, which is what allows us to make this substitution. A tangential is equal to A sub x. Okay, and I hope that makes sense. But I just wanted to kind of emphasize where that came from. So now you'll notice that we have an expression for the force of static friction. And so now this is no longer an unknown. We can make this substitution here. We can substitute in for f sub s in terms of A sub x, and then we can solve for A sub x in terms of moment of inertia and radius and mass and theta and acceleration due to gravity, all of which are quantities that we know. Okay, so that's pretty cool. How do we go about actually solving this problem? So what we're going to do is we plug in for the force of friction, and it's negative mg sine of theta plus I A sub x over r squared equals negative ma sub x. We rearrange this so that we can get all of the A sub x factors on the same side. We then pull out A sub x here, and then we can multiply both sides by -1. So we're dealing with just positive quantities on all sides, which is very nice. We don't want any negativity in these videos if we can avoid it. And then what we can do is further simplify this and solve for A sub x. So we have A sub x, we divide both sides by this whole mess here, and we end up with A sub x equals mg sine theta over I over r squared plus m. Okay? So if we multiply both top and bottom by 1 over the mass, just to get rid of the mass here and get rid of the mass here, we find that the acceleration A sub x is equal to g sine theta all over the moment of inertia over m r squared plus 1. But something kind of cool happens here. notice that we know what the moments of inertia are for each of these individual objects, right? And those moments of inertia all include this mass term. So if what we do is we substitute in for I here, you will notice that the mass term will actually cancel out. That mass ends up dropping out of this particular calculation, as does in fact r squared. Earlier I'd said that it might depend on the radius. Acceleration of the center of mass might depend on the radius. Oops, it doesn't actually end up depending on the radius. The acceleration of the center of mass in this case is entirely dependent on which planet we're on and the angle at which the ramp is slanted. And it's also dependent on what kind of shape you're using, because that's what you're plugging in for moment of inertia. So moment of inertia gets plugged in here, and these are the accelerations of the center of mass. You will notice that the highest acceleration, you'll notice first that the acceleration is not dependent on mass. You will also notice that the highest acceleration is that of the sphere. That's 5/7 g, as opposed to 2/3 g for the disk, as opposed to 1/2 g sine of theta for the hoop, which broadly is the same, or is exactly the same as what we would expect from what we saw in slides 13 and 14. So the sphere will accelerate the most, the hoop will accelerate the least, and the disk will accelerate somewhere in the middle, meaning that the sphere reaches the bottom of the slope first, followed by the disk, followed by the hoop. And again, that's not dependent. And what we're assuming in this case is that the angle, the slope on which they're falling, is the same in every single case. So that's really cool. You can plug into this expression. We saw how this expression came to be, and you find something that's not dependent on mass. It's only dependent on what planet you're on and what that angle of inclination is. Okay. So that's all very nice. How do we handle work and power in rotational motion? We've talked about kind of similarities between the linear case and the rotational case elsewhere in the Chapter 10 notes, and this is no exception. So the work that you're doing in rotational motion is equal to the change in kinetic energy, which is equal to 1/2 I omega final squared minus 1/2 I omega initial squared equals 1/2 I omega final squared minus omega initial squared. And we're just dealing in this case with work that's happening with things moving just in a circle. We're not thinking about translational motion just yet. We're just thinking in this case about work in rotational motion, right? So if you remember from the kinematics equations, the rotational kinematics equations, and the analogies to the kinematic equations in the linear case, that omega final squared is equal to omega initial squared plus 2 times alpha times delta theta. And we can therefore rearrange this, and we find that omega final minus omega final squared minus omega initial squared equals 2 alpha delta theta. All right. So the work, we go ahead and say this whole expression, we plug this in here. So that's what we're plugging in. So we have 1/2 I times 2 alpha delta theta, and this 1/2 and this 2 will cancel out. So that's what we end up with. We also should remember that the net torque is equal to the moment of inertia times the angular acceleration, which is, hey, looky. That's that thing right there. All right. So that then allows us to make a substitution that the work is equal to the net torque times delta theta, or change in position, which should kind of ring a bell when we say that, work is also equal to force times distance, right? So in this case, the torque is sort of serving in the stead of force when we're dealing with work and power in rotational motion. Now, we can actually take this analogy further. You notice that work was equal to the integral of the force dx, right? And you can indeed say the same thing when it comes to torque. The work is equal to the integral of the torque between the initial position and the final position. Okay? So if you have constant torque, if in other words this torque is not a function of the position, what you can say is that the work is equal to the torque times the final position minus the initial position, and that's irrespective of whether you're using this definition or the integral definition. Okay? So whichever definition you use, this is going to be work when torque is constant. Now, be careful. The torque may not be constant. It may be a function of theta. It may be a function of theta. And if that's the case, then you should go and use the integral definition. So that's just a word of caution, is that torque is not always constant. But if the torque is constant, then the work done by that torque is equal to torque times the final position minus the initial position. And if we're thinking about power, as you'll recall from chapter 6, the rate at which the work is done is the power. And the power is equal to d work, dw over dt, the derivative of the work function with respect to time. And what we can say is that in the torque case, that is equal to the torque times the change in position over time. So d theta over d theta by dt, that derivative. But this derivative, you'll also note, is an angular velocity. It's the change in position over time, which is better known as the instantaneous speed. And so power is equal to torque times the angular velocity. Right? So let's take a sample problem here. Let's say that we have a 32.0 kilogram wheel, which we're going to treat as a thin hoop with a radius of 1.20 meters, and it's rotating at 280 revolutions per minute. It must be brought to a stop in 15.0 seconds. For some very, very important reason, it must be brought to a stop in 15.0 seconds. Why that is, the problem doesn't say, but trust me. Anyway, how much work must be done to stop it, and what is the required average power? And we want absolute values for both parts. So the initial angular speed, the first thing we want to do with omega is put it in terms of radians per second. And it's given currently in revolutions per minute. So to do that conversion, what we want to do is we have 280 revolutions per minute, and we use our old friend dimensional analysis to take revolutions to radians. We remember that the number of radians in a circle is 2 damn pi. So 280 revolutions times 2 pi radians over 1 revolution. The revolutions cancel, and we're now happily in radian land. Right? How about minutes? We want to convert minutes to seconds. So we have minutes in the denominator. We put it in the numerator over here. We have that conversion factor of 60 seconds to a minute. The minutes drop. And then we end up having 280 times 2 pi times 1 over 60 seconds. And we end up with 28 pi over 3 hertz is the initial angular speed. And then we remember our handy formula for work, which popped in before we converted the angular speed. So, still very important. And we say, all right, so the rotational inertia of a thin hoop is mr squared. That's in table 9-2a. And what we can say is that we know what the mass is. That's 32 kilograms. That's given. right? And then we have the radius. The radius is given. So that lets us calculate the moment of inertia as 46.1 kilograms times meters squared. So the work done is simply the final angular velocity that we want here is 0. All right. And the initial angular velocity is given by 1/2 times the moment of inertia, 46.1, which we calculated, times the radius, times the angular velocity, omega naught squared, and that's 28 pi over 3 seconds. And we have that whole quantity squared. So we know that the work done has to be 1.98 times 10 to the 4th joules. Okay? And then just to make sure that our units are correct, we have kilograms times meters per second over seconds squared. So that's kilograms meters per second. We have seconds in the denominator here because this is given in hertz. That's 1 over seconds, or s to the negative first. So that becomes squared in this case. So it's kilograms times meters squared over seconds squared. And that's the same thing as kilograms times meters over seconds squared times meters. And a kilogram meter per second squared is the Newton. So you have newtons times meters, and a Newton meter is a joule. Okay, so we're in good shape there, just kind of as a reality check. And if we're talking about power, that's going to be the absolute value of the work that has to be done over the time over which we're doing this. So that's 1.98 times 10 to the 4th joules over 15 seconds is 1.32 times 10 to the 3rd watts. Also notice that because we were asked for, the absolute value, this quantity would be negative if we were not asked for the magnitude, if we're not asked for the absolute value. And why is that? Well, very simply, because we're slowing the wheel down. So we're getting rid of the rotational kinetic energy, or we're reducing the rotational kinetic energy down to 0, which is the definition of negative work. Okay? All right. So this is just a big handy table interrelating the analog between linear counterparts and rotational variables, because you can kind of think of rotational motion as linear motion that's happening in a circle. That's kind of a weird way to think about it, but there definitely are analogs. So in position, what we used to call x, or what we call x in the linear world, we refer to as theta in the rotational world. Velocity v is called omega in the rotational world. That's the rotational velocity, or the angular velocity. Acceleration, a, becomes alpha, or angular acceleration. Mass, m, becomes I, the moment of inertia in the rotational world. Again, much as a mass is a resistance to a change in a state, it's a resistance to being either sped up or slowed down in a linear world or in a linear fashion. The moment of inertia is the resistance to being spun, or the resistance to having the motion in a circle being changed. So it's basically a different kind of inertia. Force, F, you can think of the equivalent in the rotational world as being torque. And if we talk about Newton's second law, where F net equals ma, instead it's torque net equals moment of inertia times angular acceleration. So again, that moment of inertia can be thought of as a resistance to being accelerated in a circle, and the net torque can be seen as a force which is acting to rotate that particular object. Okay, work is equal to the integral of the force dx in the linear world, but in the rotational world, work is equal to the torque times d theta. Kinetic energy in the linear world, k is equal to 1/2 mv squared. In the rotational world, k is equal to 1/2 I omega squared. And in cases where we have both things happening at once, where you have both a linear translation and a rotation happening at the same time, the kinetic energy is going to be split up between a linear component and a rotational component. Okay? Power is force times velocity in the linear world. And in the rotational world, power is equal to the torque times the angular velocity. Linear momentum, which is a quantity that we met in the one of the previous chapters, in chapter 8, momentum is equal to m times v. But in the angular world, there is something called angular momentum, and angular momentum is equal to the moment of inertia times the angular velocity. So what exactly is this quantity of angular momentum? What exactly does that mean? Well, tune in for the next lecture to find out. Thank you very much, and I will see you next time.